And thanks to Yuri and Russell, who isn't here today, I don't think, for inviting me to come and speak to you about climate modelling and climate change. And look, just before I get into that, I'll just say just a little bit more background than what Yuri said there. Yes, look, I did train as a physicist, and in fact I'd still regard myself as a physicist, as an atmospheric physicist, but I did have this quite dramatic change from particle optics through to climate change. And look, it's been a tremendous career development for me, and I've really enjoyed it. I'd encourage those of you who are looking forward to further career developments to consider places like CSIRO and the Bureau of Meteorology as possible career options. We advertise from time to time. I mean, things are a little bit tight at the moment, but we advertise from time to time for people to come in and join our research section working on, say, climate modelling or climate change. And often we'll take people without particularly strong background in that sort of thing, as long as you've got a good background in physics. So keep an eye on that. Okay, so I work at Corker, which is a research organisation of about 300. And it's a collaboration between us and CSIRO, and that's, Corker stands for the Centre for Australian Weather and Climate Research. Now what I'm going to talk about today is climate modelling, and just a really brief rundown. I'm happy if people want to stop and ask questions. I always find it difficult to know what level to pitch this at. It's not going to be a terribly technical presentation. Quickly, some motivation, why we need climate models, what is a climate model, basically how good they are and how do we know, what they tell us about the past, about the recent past, what they project, of course, which is a critical thing we want to know, what are we confident of, and where are the big uncertainties. Now, I'm aware a lot of you probably work in areas where you do modelling. Some people will know a little bit about climate modelling. Probably quite a lot of you might know a fair bit about climate change. In fact, I hope you do. Okay, so just quick motivation. The climate is changing. Here's the global and Australian temperature records for the last 150 years or 100 years, and we can see them going up, and there are wiggles in here, so one year is not necessarily warmer than the previous year, but we've just set a record for the warmest year on record in Australia. So temperatures are going up. At the same time, we're seeing changes in glaciation. For instance, the Larsen ice shelf broke off about 10 years ago. Sea level is rising. We're getting melting in Greenland. There are a lot of changes going on. I'm not going to labour this point because this isn't really what I'm going to talk about, but if you look at snow cover, permafrost, Northern Hemisphere sea ice, you see a consistent picture of global warming that's taking place. And IPCC, which is the Intergovernmental Panel on Climate Change, which is, if you like, the gold standard in assessment of climate change science. Every year, every 7 or so years, they get together and assess the state of climate change. They concluded in 2007, warming of the climate system is unequivocal. It's really beyond doubt. At the same time, we have records like this. This is this beautiful record of CO2, carbon dioxide levels in the atmosphere from Hawaii. And we take similar records from Cape Grim in Tasmania, on the northwest coast of Tasmania, and it shows that carbon dioxide levels are going up. And then you can also look at ice core data. For instance, this is for the last 10,000 years, and you see we've got this recent spike. And we know that carbon dioxide levels are higher than they've been for the last 800,000 years or so. So the question is, we've got this carbon dioxide and other greenhouse gases going up. We've got this warming. Has that caused that, or is that warming caused by something else? And also, what's going to happen next? So this is why we need climate models. We need understanding of the climate. We also need climate models. So if we're going to go about modelling the climate system, we need to do a lot of things. The climate the Earth's very large, physically very large, very complex, with a huge number of scales that processes occur at. We need a basic understanding of atmospheric predictability, fluid dynamics, because it's a fluid dynamics problem across the sphere. Phase changes, for instance, precipitation of water, radiative transfer, there's a critical. Interactions within that system, for instance, El Nino, which is an interaction between the atmosphere and the ocean, I'm sure you're all aware of, and so forth. So what I'm going to do is break these down just a little bit and first of all look at the basic fluid dynamics, but I'm not going to go into any of it in a lot of detail. Firstly, some of these aspects I'm not a particular expert on, and secondly, I want to give you an overall flavour of how the models are built, what they're good at, how we test them, and so forth. Okay, so really these are the only equations I'm actually really going to show. But just at the core of general circulation models are what are called the primitive equations. They're not primitive, but they're just the basic equations of fluid dynamics, essentially, applied to a sphere. And we have, at the heart of every general circulation model, we have 5 equations here. And basically, they're based on conservation of momentum. So, for instance, the change in the wind depends, the wind vector here depends on Coriolis, depends on the pressure gradient, and depends on dissipative forces like dissipation or subgrid scale processes, which I'll emphasise in a moment. And then we have, of course, conservation of energy, conservation of mass, conservation of water substance. Now this in a sense is, to solve these on a sphere is essentially a solved problem. This is actually called the dynamics, so it's actually called the dynamics of it, but of course it's physics here. But this is referred to as the dynamics of the process. There are these little kickers here though, these terms here, like this F term and this Q term, and they're in the jargon are called physics in the climate modelling, and we'll come back to them in just a minute. To solve the dynamics...
So sorry, when you say horizontal moment...
I'm sorry?
When you say horizontal moment,
yeah,
you're looking at vectors in V that are only in the X and Y plane.
Yeah.
So you're not worried about vertical...
Well, there's an assumption called that it's in hydrostatic balance, and that is that vertical, this hydrostatic equilibrium here, there's an assumption that vertical accelerations are small. And if you look at the large scale, for instance, synoptic scale of highs and lows, that's a very good approximation. If you're worried about severe thunderstorms, that's not a good approximation, but we're dealing with much larger scales here. Okay, so these little terms here, this F, Q and S, represent things like, for instance, in F, represents things like turbulence, dissipation of momentum. This Q term represents things like convective scale transport of heat. Let's come back to them in a moment. First of all, the equations are solved on a sphere, and this can be done in a number of ways. And I'm not a particular expert on this, but there are quite a number of ways you can set up this problem to actually integrate these primitive equations, so that you can start with initial conditions and then move ahead. So in other words, if you know what the atmosphere looks like at the beginning, you can time step ahead. Now, different possible approaches can be done on this. For instance, you can divide the globe up into a grid, lat-long grid. You can reduce that grid by seeing it get sort of a bit crowded at the poles, so you can do things to reduce the number of points you have here. Or you can use clever grids like this, for instance, dividing the globe up into different shapes. And there's a very nice CSIRO model that actually is called the cubic conformal model that has a really nice sort of soccer ball type grid. These can be then solved, say, by finite element methods or spectral transforms, where we take spectral transform of the particular field, and then we can step that forward in time. And that's got some nice numerical properties and so forth. In the vertical, we have to be a little bit careful about what we do, because if you just have a horizontal vertical grid, then you bump into mountains and things, and that causes problems with solutions. So it tends to be a terrain following grid that moves up and down over the mountains. So I'm not going to go into a lot more detail on that, because I want this really to be rather technical talk, sort of a flavour of as I said, of how these are tested and so forth. So let's look at this parameterization issue, this issue of what we can and can't resolve. If we have a high in the byte here, we see it's big. Okay, it's called synoptic scale in the terminology. And actually, when I first worked as a meteorologist, there was a little saying there that was, high in the byte, forecasters delight. And actually, forecasters love it when there's a high in the byte because it's a very stable and easy to forecast situation. But in any case, that's beside the point. What's important here is that this is a big system, thousands of kilometres across, and we might have a grid spacing in our model of maybe 100 kilometres or so in the horizontal. And so we can easily resolve this. And so models are particularly good at representing, say, the daily movement of high and low synoptic systems. But there's a lot that happens in the atmosphere and in the climate generally that we can't resolve like that. Here's this sort of beautiful thunderstorm here. Obviously, a 100-kilometre resolution grid is not going to represent all the processes that are going on here. So there's interaction with radiation, there's turbulence, there's condensation, and then there's precipitation. These things happen at a much smaller scale, but we know these are absolutely critical. This is what happens with convection and so forth is absolutely critical to the dynamics and physics of the atmosphere. So we have to represent these in some way. And in models, they tend to be represented in a, if you like, a sort of a simplified sub-model. But that sub-model is often based on semi-empirical things from observations that have been taken out in the field. Some processes, for instance, of condensation, very complex and not properly understood. So this is called, the jargon is parameterizations. I'm using in many areas, of course. And just some examples of parameterizations here. So the basic idea is we unresolved physical processes. We have to represent them in some way as they relate to this 100-kilometre grid. And examples of parameterized physics, dry and moist convection, so thunderstorms that occur, cloud amount, cloud optical properties, radiative transfer, which of course is occurring at a molecular level, boundary layer transport, surface energy exchanges, and so forth. So this is the weaker side of models, and we'll come back to this. Okay, so a coupled model. What might a basic coupled model look like then? So a coupled model will contain components of the atmosphere, for instance, built along the lines I've spoken about, an equivalent for the ocean, and then components of sea ice and land surface. Okay, this is why if we refer to a coupled model, we'd really need representation of these processes. There are other issues going on though, and one I would say is the carbon cycle. So there's a complex interaction in the long term between carbon that's in the atmosphere, for instance, its uptake in the ocean, or its uptake by plants or soil respiration, this kind of thing. This has become a very important part of modelling. So where we're getting to is a model of this kind of complexity that has representations of the atmosphere, ocean, and so forth, but it also includes dynamic vegetation, in other words, representation of plants taking up moisture and taking up carbon dioxide. Might have an ocean carbon cycle that will contain biology in there, because a lot of the take-up of carbon is biological. Components of atmospheric chemistry and aerosols, sort of tiny particles of dust and soot in the atmosphere that interact very strongly with radiation and also can form sort of rain nuclei. So we've got this particular picture is one that's really shown a lot in our area, and actually it shows sort of the evolution of Earth system models, and I would actually say it reminds me of this sort of progress. This is sort of a bit of summary of where the rapid development that's taken place, and actually it's been a really exciting time to be involved in climate modelling, because climate models have changed enormously from 25 years ago, from really quite primitive models right through to these very sophisticated, what we call Earth system models. So in the mid-70s or the 80s, we had really basic systems, even without an ocean. And these components have been added one by one until here or up here we've actually got some representation of all these interacting processes. The future includes things like ice sheets, even moving to cloud resolving models, so bring the resolution right down so you can try to resolve these explicitly. And people even talking about putting human interactions in other words, to actually making the humans interact with those models. So we're arriving at something we would call an Earth system model, would be the jargon.
Robert?
Yeah.
Just a question. On this evolutionary picture, how does the number of parameterizations in your models scale with time?
Well, the things we basically parameterize don't really change that much. So we need to parameterize convection, and even as we add different components here, then the parameterizations in the atmospheric model don't change that much. But if you were then add a carbon cycle model, you have to start parameterizing, if you're talking about the ocean, then maybe phytoplankton and zooplankton interaction that are responsible for uptake of carbon from the ocean and so forth. So it's a good question in the sense that the unknowns that we have, or the things that we're least confident of, kind of multiply out if you keep adding these different components. So as you go to a more and more complicated model, it becomes more difficult to understand, and it also, you don't know what's happening in the depths of this model. And there's a danger that there are assumptions in there that you really can't justify. So it's a real problem, actually. And a model like this now is developed by vast teams of people interacting across institutions and so forth. So it's really become quite a management exercise as well. So the applications, and people are very aware of these, I imagine. We have a model at the Bureau of Meteorology that we co-developed with CSIRO called Access. We run that several times a day for weather forecasting. That's where the weather forecast comes from running the atmospheric model alone. We have a coupled model, and that is used for the seasonal predictions that you'll see from time to time. We say it's going to be wetter or warmer or whatever in the next 6 months. So that's run out to about a year. And of course we have climate modelling. Now, just before I go, I'll just for completeness say this, and I'm not going to talk about these in any more detail, but just to let you know, you can also nest models within models. And a popular device is a regional climate model where you say, this 100-kilometre resolution is not enough for me. And our stakeholders often want this kind of thing. In fact, we recently had a project where we were projecting climate change for the Pacific Islands. And a 100-kilometre resolution doesn't represent, say, the highlands of New Guinea terribly well at all. And in fact won't represent Fiji at all. For instance, so their island won't actually appear in a general circulation model. So if you're producing projections for them, their island's not even a dot in the model. So people, we can apply here a regional climate model, which might be a much tighter grid mesh in there that we can embed in the global climate model. And this is useful for example, for resolving small islands and topography and this kind of thing. There's a strong caveat. This is called dynamical downscaling. There are different ways you can downscale, if you like, to scales you might be interested in. But an important caveat here is they look a lot better because you can see there's all this detail that comes out of them. But we don't really trust a lot of that detail anymore because they've got the same parameterization uncertainties that global models have. I won't talk any more about them. So I'll show one movie. So this is a coupled ocean atmosphere general circulation model, actually an old CSIRO model. This is 20 years or so of monthly means, and it's not climate change. It just shows the sort of variability you would see, you might see as that the models generate from spontaneously, if you like, from the interaction between the ocean and the atmosphere. So you see some ENSO events occur, which is sort of warming across here in the Pacific. So if you run this ahead, you see, for instance, a cool event there on the equator. Not much there for a very strong warm event there, followed by a cool event. And you see sea surface temperatures moving along. And this is variability generated within the model itself, not imposed. And so if you marry these models, they do generate some of the important modes of variability that we want to be able to capture. Okay. So that's what models are basically. Now, Joe, quick section on model evaluation, and this is an area that I've been heavily involved in. And of course, we need to be able to be confident that these models are useful for the tests that we're going to use them for. So we have to evaluate them. And in an ideal world, and probably with the kind of models that people here, if they're developing models, would be using, you'd run your model, you'd make a projection, you'd test that against the observations, then you'd refine your model, so forth, and you'd be in this cycle. Now in climate change, this is not possible. We can't wait the 50 years or 100 years for this and then, oh, okay, the model was bung, we refine the model. So I would say this is a luxury restricted to weather forecasters. And weather forecasters do this every day. They run the AGCM, they make their projections and so forth. So they can do this testing every day. But I actually put a question mark on this because maybe we can do this. So there are a few ways of testing models. The best way, of course, the way that it is usually done is just to compare the models to the current climate. And you say, how well do they represent things we know are important in the current climate? If they do a good job of that, and they do a good job across a whole range of these things, then we might be confident that they include the physical processes we know are important for climate change. So that would increase our confidence. So I just show here observations, and this is not a single model, but this is an average of 24 different models. And I'll talk about this CMIP beast a bit further down the track. But this is 24 different, separately developed general circulation models, coupled models, all run with similar conditions and averaged out and see what they get. And you see, compared to the observations, the models do a really fantastic job in representing the current temperature of the planet. Okay, in fact, the pattern correlation between these is about 0.99. So models can actually represent current climate distribution very well. In some senses, that's a bit cheating a bit though, because we're putting a lot of information into the models for temperature. Okay, we're putting a lot of we're putting the configuration of all of these, continents and so forth. We're putting the astronomy in. We know where the sun is and this sort of stuff. So let's give it something harder. And the harder one people want to know about is rainfall. Okay. Now, to get rainfall right, you've got to do a lot of things. Remember, that's not represented by the large scale. It's a parameterized thing. But you have to be able to get the large scale circulations pretty well right. You've got to get evaporation taking place where it needs to and water being advected to the regions where it needs to. You might have to get monsoon circulations correct there. You have to get some kind of convection happening and rainfall come out. Now, a lot of those are parameterized, so you've got to get a lot of things right in the model to get rainfall right. So how do models do with rainfall? And this is that same 24 models, and this is now annual mean rainfall. The observations and these 24 models here. And for a start, this is a really interesting pattern. You can sort of stare at this for a long time, but the pattern of rainfall is very distinctive. There's this very strong tropical maximum called the intertropical convergence zone across the Pacific. There's this very nice maximum here that stretches down to the Pacific and affects a lot of these Pacific island nations. And then we have these sort of dry areas, for instance, over Australia and other areas. Then these sort of mid-latitude rain belt and so forth. And how do models do? And actually, they do pretty well with the overall features of this. They get this major peak here. They get this these dry areas. But for instance, see the tilt of this is not quite right here. Some of the rainfall that occurs over the Amazon is sort of not occurring. So, there are features, there are strengths and weaknesses. So the models do a reasonable job, but not a perfect job with representing something like rainfall. In fact, if you go to individual models, you'll find some really quite surprising. Some models are really quite skilled. Some models have some really surprising results. So I won't talk any more about model evaluation. Sorry, you have to shout that out. My hearing is not good.
So you mentioned 24 models. and you said they're all quite similar. So would they differ because of physics or because of like numerical?
Good question, and the answer is both. They might have different numerics. One might be a spectral model. One might be, a grid point model. But the dynamics doesn't really matter that much. The critical difference between them will be their parameterizations. For instance, how they parameterize convection. So they have scheme A, which is based on this, and these assumptions. This has scheme B, and then they have a whole lot of parameterizations, and then they interact together in a complicated way. So it's the parameterizations that are really the critical, but you can't ignore dynamic differences as well. Okay, so I'll talk no more about model evaluation of the current climate, except to say model evaluation is extremely extensive. Really, there's an awful lot, a lot of papers written on this and a lot of analyses on this. People look at winds, monsoons, El Nino, decadal variability, land surface, sea ice extents, and so forth. And the conclusion of reliability from, or on skill from the IPCC in 2007 was models have significant and improving skill representing current climate and modes of climate variability. Okay. So models can do an okay job with the current climate, but then what if you give it a kick? For instance, we increase CO2, is their response reasonable? And then we have to think a bit more carefully because, and we need some kind of, I normally actually ask people now for a suggestion. I normally give it to an audience like this, but anyone got an idea for a kick that occurs from time to time that would really give, we could test climate models with their response?
Things that happen in reality.
What's that?
Like things that happen in reality, you mean?
What's that?
Non-human things that happen in reality, you mean?
Yeah.
A volcanic?
Yeah. Perfect. Volcanoes. So a really nice way of testing these models is to see how they respond to volcanoes. Okay. Now, a big volcano, we haven't had a big volcano for a long time. But in the 1990s, Pinatubo went off and caused about 0.5 degree of global cooling that lasted maybe for 2 years. So a big volcano that injects a lot of sulfates up into the stratosphere can really have a significant climate effect. So what you can do is you can test your model. For instance, here we've got just a single model, but here's the temperature after the volcano went off. Here are the observations in black, and here's a single model that you run. Not all models match it this well, which you give it your best estimates of what that forcing was, and you get the response that comes out. Just for the sake of time, I'll just quickly move on. There are other ways you can test them. The paleoclimates, for instance, we have idea of what the last ice age looked like, how they responded to that. And there's actually the observed warming record. Now, IPCC, the Intergovernmental Panel on Climate Change, first gave projections in about 1990, the first assessment report. And so they projected here, and of course, since 1990, we've had nearly 25 years have occurred. And over that time, here are the projections from IPCC, and the climate, global temperature's gone up and down here. In fact, it's still sitting at about this level here, but it's encompassed within this range of projections. So that also gives us some confidence that the projections from these, albeit primitive models back in 1990, has come close to reality. So IPCC concluded there's considerable confidence that climate models provide credible quantitative estimates of future climate change, and it comes from foundations in accepted physical principles down to the primitive equations and their ability to represent observed features of climate change. So let's now quickly apply them. Okay, so remember we had two motivations. Go back to that slide a while back which said, has that CO2 increase caused the warming that we've seen, and what do the projections look like? So let's quickly address the first one. So we've seen temperature changes. Has it been caused by greenhouse gases? Okay. So what we show here is a plot. The black line here is the observed warming up to just after 2000, or observed temperature changes, global temperature changes. And there's a fuzzy light blue lines in here, which are a whole lot of these 24 models, okay? And they're run with our best estimates of what we call natural forcing, okay? So they've got their own internal variability, and we put in our best estimates of volcanoes into them, and any solar changes, sort of solar input at the top of the atmosphere, any solar cycle changes that we've seen over the last 100 years, our estimate of that. And the blue line is the average of the models, and you find that the models don't represent this warming that we see towards the end of the century. If you put in our best estimate of what greenhouse gases have been and what sulfate aerosol emissions have been, then you get this. Now here's the same models, and then the red line is the average of the models. And you see there's a much better agreement with the observations. And there's other evidence as well, like patterns. But this is what's called the attribution question. So we could use these models by combining the observations and the models. You can address the question of whether anthropogenic emissions have been responsible for the climate change that we've been seeing. Yep.
Robert, has there been any tuning of the parameters?
Hey. People always tune their models, okay. But they don't normally tune their models to get this. What they tune their models, there are unknown parameters in there, okay, like in your convection, whatever. And what you can do is some of these are better known than others, and people will tune those parameters to get things like the top of atmosphere radiated balance correctly, so the models aren't running off somewhere. It's impossible to tune a model, though, to say give a good decadal variability, or to give good monsoons, or to give, and it's hard to tune a model to give this sort of response. But yes, there is a degree of tuning that takes place, and that does muddy the water somewhat. Okay, let's quickly move to the future then. This is a pretty rapid, hope not too rapid, look across the models and their applications. Scenarios, so future emissions, so we want to know what can happen in the future, and this of course requires crystal ball gazing. So what climate modelers do is they consider scenarios of the future, and a scenario is like sort of a what if. It's a what if population does this, and there's this level of economic development, and there's this level of international exchange, and this, you can play games with these what ifs and look at what future emissions might be. There's a huge literature of that and a huge science of that all on its own. But what we do for climate projections is these models are very expensive to run. They're huge, and it's a major effort to run them. You need huge computers and you need a lot of time. So we can't run 10,000 different scenarios for the future. So they're boiled down into just a few families, these RCPs, which are called representative concentration pathways. So these are projections for the future, if you like, of how this radiative forcing, so the top of atmosphere imbalance, might look like from greenhouse gases over the next 100 years or so. So underlying this pathway are emissions of methane and emissions of nitrous oxide and this kind of thing. And they're divided into these things. The jargon is, so an RCP is representative concentration pathway, and 8.5 is, by the end of the century, there's 8.5 watts per metre squared forcing at the top of the atmosphere. In other words, an imbalance compared to pre-industrial times of 8.5 watts caused by the extra greenhouse gases there, trapping that extra heat. And we have RCP 8.5. So these know about, these have got different assumptions about mitigation. For instance, this is sort of very little mitigation done, whereas this RCP 2.6 would require not just that we reduce emissions, but towards the end of the century, we actually actively uptake carbon dioxide from the atmosphere. Okay. So I'll leave you to guess, you know, assess for yourself which of these you think might be the most likely that path we go down. But for climate modelers, we take these different scenarios and we give them to policymakers and say, if you do this is what you're going to get out of the thing. A quick aside, we have something called CMIT5. I talked about this before. We run a lot of models. There are a lot of models internationally now. CMIP5 is a coupled model into comparison project, and before each of the IPCC reports come out, all of the different modelling groups get together in the world and they run a series of similar experiments with similar forcing. Now, I don't want you to worry too much about the detail here. The take-home messages are there are a lot of models. Okay, we've got nearly 50 models worldwide now that take place in this, and they run a lot of experiments. And one of the experiments is RCP 8.5, but they run a lot of other experiments that allow these models to be compared and so forth. So what do the projections look like then? So if you run these things ahead with CMIP3, and you can probably forget this for a moment, but CMIP5, this represents the climate change that we've seen up to this point. Remember, we saw this black line before. And then you initiate these models just after the year 2000, and you run them with these different RCPs, which you've got different concentrations of carbon dioxide and etc. And so for an RCP of 8.5, which is sort of like a business as usual, you come out with this warming of about 4 degrees. And the heavy red line is the average of what the models say, and this red sort of cloud around it you see is the standard deviation of the different models. In fact, there are 22 models in this ensemble. And then you see that what happens depends very much on what the future scenarios are. And I'll just highlight here then a few things we can glean from this plot. And I'd say this plot, it's a simple plot to put up, but it's a result of an enormous number of experiments by an enormous number of groups and all this model development and so forth. So it's sort of the distilled result of a huge international effort. Over the next few decades, you see, ignore the yellow one, they cluster together quite closely with a warming of about 0.2 degrees per decade, although there will be natural variability in there. And you see what happens the next few decades doesn't really depend very much on what we do with emissions. And that's because a lot of the warming is already in the pipeline. And the difference between emissions takes a while to kick in. So if we do something dramatically different now, we're not going to see the result of that for quite a while. So in a sense, it shows that what is going to happen soon is not sensitive to that. At the end of the century, you might get a difference in the warming maybe of a factor of 2 or so it's much bigger. And there's this third one here, which was run by holding concentrations, carbon dioxide concentrations fixed at year 2000 levels and just seeing where we go. And the world continues to slowly warm up because we're out of radiative balance still. The ocean's like an enormous flywheel. It's taking a long time to warm up. So we've still got extra warming in the pipeline even if we were to stabilise concentrations. I won't have time to. The last thing I want to talk about, maybe for 5 minutes or so, is actually, remember we promised we'd get to what we're confident of and what the biggest uncertainties are. Okay, so if you look at this, you can say, well, why the large uncertainty and how much does that matter? And it matters a lot because our projection might be 4 degrees, but remember this is just a standard, so a third of the models are actually outside this range anyway. This range says it's probably between 3 and 5 degrees. Now, a 3 degree temperature change is going to be a lot, but a 5 degree temperature change is really a lot. So you really want to know where we're going to lie in that range and why the uncertainty is there. So the question is, what causes that uncertainty? Now, just a quick digression then. Just looking at the basic physics of the planet and doing this on the back of an envelope. You sit down the back of an envelope and come up with the warming that you would get in a very simple planet very, very easily. If you double the amount of carbon dioxide in the atmosphere, that produces a 4 watt imbalance at the top of the atmosphere called radiative forcing of 4 watts. We're very confident of that. You can measure CO2 properties in the lab. You can measure this with satellites. So it produces a 4 watt per metre squared imbalance if you just say instantaneously doubled CO2. The climate system, if the climate system just responded in a very simple way, nothing else changed except the planet just warmed up. So the temperature structure didn't change, the amount of snow and ice and stuff didn't change. You can figure out how much it would have to warm up to get rid of that. just by simple Planck cooling, sigma T to the fourth. Okay, so you differentiate that, you find that it's about 4 watts per metre squared per degree. So if you just warmed up the planet, it would radiate out that extra trapping with 1 degree warming. So our sort of basic response here would be about 1 degree. But if you look at what climate models give, they give this very big range, remember we saw, and in fact if you just double CO2, run a very simple experiment, they give a warming from about 2 degrees here to about 5 degrees. So give a much bigger warming for that, and they give a big range. And the question is, why the warming, why the bigger warming, and why the range? And it's because of feedbacks in the system. And you people here, physicists, you're very familiar with the idea of feedbacks. It's a really nice, simple conceptual model to think of the planet as a simple, if you like, we can think of it as an amplifier here. And we have a climate feedback, which is a process that responds to that initial kick that we give it, changing properties of the atmosphere or ocean, which further change the radiation balance at the top of the atmosphere. And a critical one is water vapour. Now, water vapour depends on the temperature there. You go to the tropics, there's a lot more water vapour, okay? You know, you can just feel it in the atmosphere. So as we warm up the planet, there's more water vapour held in the atmosphere. It traps that heat, and it's a positive feedback. So a useful way of thinking of this is as an amplifier. And you say, instead of this simple system, we can regard that temperature change of 1 degree, if you like, the open loop gain of this amplifier. And we consider the climate system with feedbacks, we give it that kick, and then as a result of the warming, we might get increased water vapour, for instance, or we get decreased snow and sea ice, which allows more incoming solar radiation to be absorbed. Cloud changes, which I'll come back to, and some temperature changes here. And using this amplifier analogy, the final temperature change is this open loop gain, a 1 over 1 minus this set of terms. Each of those are, in a sense, that fraction of the Planck cooling that is offset by that increase. So for a 1 degree temperature increase, the amount of water vapour traps about 2 watts per metre squared. Okay? About half of the Planck cooling is offset immediately by water vapour changes. So what you find is, because relative humidity doesn't change very much in changing climate, to the best of our knowledge, as you warm up, you'll find that extra feedback gives a 0.5 here. So straight away, from the increase in water vapour, you get this doubling of climate change. Okay? And so A, it gives us that kick into the region that models are at, and B, it sensitises it, if you like. Because since this is already 0.5, if you add other positive feedbacks in here, and we know there's a positive feedback, say, from snow and sea ice reduction of maybe 0.1, if clouds also give another, you can see that you can rapidly get quite a high temperature change. Now, we're not close to runaway greenhouse warming here, but this is what gives it now I'm running out of time here, so I just say clouds are the big unknown here. We don't know how clouds are going to change. And although we understand water vapour feedback very well, I'll just convince you that the biggest uncertainty comes from the way clouds might respond. And the reason why clouds are the problem is A, clouds are parameterised. Okay? So we've got simplified physical assumptions in there. The second reason why cloud response is secondly, clouds are really radiatively important. Okay, they reflect solar radiation and they trap outgoing long-wave radiation. And thirdly, you often get these offsetting effects. So, say compared to the present climate to the warmer climate, say the cloud amount increased, you'd see in the long wave that would be a positive feedback, would trap extra radiation. In the short wave, it would be a negative feedback because it would reflect incoming solar radiation. And clouds can change in complicated ways. The amount, the height, how thick they are, what their total water content is, how much of that's frozen, cloud types. And you see these are often different signs. So the bottom line is that cloud changes and their impact can be extremely complex, And the final result is this sort of small result of these large offsetting terms. Okay. We think cloud feedback is positive, but we're not certain of it. I want to say that models can give very different responses. Here's a model with a very strong reduction in low cloud. As you warm, here's a model with a very strong increase in low cloud. Look, I've just about run out of time here. What I would say is we need to be able to estimate climate sensitivity, okay? And there are a number of different ways that we can do this. One, we can, and this is for us then assessing what that climate change might be. And the science community has gotten together and they've pulled all these different techniques for estimating climate sensitivity. One, you can just look at all those 25 models you've got or 40 models you've got and see what range they give. The second thing is you can actually look at the observations and what's changed. You can say we've warmed up this much, we've had this much forcing, what sort of sensitivity do you get? And a third very clever way, which I would like to mention, is called a perturbed physics ensemble, where you get a single model and you say, okay, look, we don't know. We don't know that, you know, about convection that well, or whatever. What are the big unknowns in here? What if we take this parameter and we double it? This is a particularly unknown thing here, particularly, can we change these between various values that are uncertain? And if you do that within a single model, you can get this lovely range of sensitivity come out of it. And that shows that the reason for that uncertainty and sensitivity is from the physics. So you can pull it all together from a whole lot of different techniques. And the community has come together and has said, okay, we use paleo estimates and we use volcanic estimates and we use perturbed physics ensembles and we use multiple models, and we get our estimate of what the climate sensitivity is to a doubling of CO2. And the climate community has done that. And this is what they've discovered over the years. This is the history of climate sensitivity range in model, or from all types of evidence we've got. In 1979, the National Academy of Science in the US, they had two models to look at. One had a climate sensitivity of 2, one had a climate sensitivity of 4. They said, all right, we'll knock half a degree off this, put half a degree on this, and they came up with a range of 1.5 to 4.5. IPCC got together in 1990, they came with the same range from more models. In 1996, same range, 2001, same range, and in the fourth assessment report in 2007, they slightly increased the bottom range here. And we've got an IPCC coming out next week, and we don't know what they're going to say yet. But so I suppose the sobering information of this is we have these models that have developed very sophisticated, from very basic models through to Earth system models over this time, and since the late 70s, we still can't really narrow that climate sensitivity down below the range that we had more than 30 years ago. So I'm just going to finish on that point. Probably I went 5 minutes over, I'm sorry. Just two things to advertise. One, if you're interested in climate change projections, actually say what they look like over Australia, there's a product that's come out. You just go climate change in Australia on the web, and we produce climate change projections with CSIRO. We're going to produce the next set of regional projections in mid-2014. And the second thing is next Friday week, tomorrow week, the IPCC fifth assessment report is going to be released. This is a major, major milestone in climate change science, okay? These assessments occur only every 6 years. So watch the press and we'll see the latest set of projections and things sort of come out next week. Okay, so thank you.
We have time for several questions, but please speak up so
Yeah, my hearing is bad, so you'll have to shout.
You said that the biggest uncertainty in the modeling is the clouds.
Yeah.
They contribute. So what kind of sensitivity do different assumptions about the clouds reveal? And if you take a model that's predicting 3 degrees warming by whatever, and then make the most pessimistic and the most optimistic assumptions about clouds, what range do you get?
Well, you saw that perturbed physics ensemble, and that's not just clouds, but a lot of it is clouds. And you can get, say, you can get a warming, say, of 2 degrees, or in fact, some of the extreme outliers up there might be sitting up 8, 9, 10 degrees. Now, for physical reasons, we think that they don't actually represent the current climate that well. So we think that we wouldn't trust those very high values that well. But the rest of that range you can easily accommodate in there. Now, it's not that we don't know anything about clouds. I mean, there are some things we're confident about with clouds. For instance, as we go to a warmer climate, we expect the clouds to rise just that little bit higher because the troposphere, if you like, is actually going to be that little bit deeper. And we're very confident of that. So highest clouds will go a little bit higher. And that will tend to be a positive feedback because in the long wave, it causes extra trapping. So there are 2 or 3 other aspects like that of clouds that we're confident of. But the big uncertainty with clouds is if you fly to the US, say, fly across the Pacific, you look out the window, there are all these little puffy white clouds. They're cumulus, they're trade cumulus, they're called. And if you go off the coast of California, you get to big decks of cloud, and that's stratocumulus decks. Now, the way models change how those low clouds affect is very different. I showed you just really quickly those models. One increases it, one decreases it. We don't understand really well what's going to happen to those low clouds. And they matter a lot because they cover a huge part of the globe. So what happens to low clouds, low stratocumulus, really matters. And we haven't got a physical handle on that yet. We don't understand that.
I gather from what you said that the uncertainty about the clouds is about the same as the uncertainty across the space of models.
Yes, it's a little less because there are other uncertainties, for instance, in how snow and sea ice retreats. For instance, some models will give a very, very rapid decrease in sea ice, others less so. So that also affects that feedback. To a lesser extent, how water vapours. Water vapours are strong feedback, so if there's a little bit of disagreement, that can have a big effect. But clouds is the bogeyman, yeah.
Yes, this is the back.
Would you tell us a bit about the state of ocean modelling and how that affects the sensitivities you get from the models?
Of ocean modelling?
Yes, because
okay.
most of it's in the ocean, I believe.
Yeah, that's a good question. I haven't talked about the ocean much. The ocean's critically important for climate change because it's the flywheel. So the way the importance of the ocean is how it affects the rapidity of the warming. If there's a lot of deep mixing in the ocean, then a lot of the heat's taken away and you delay the warming. If you look at the amount of warming that we've had since pre-industrial times, something like 95% of it's gone into the oceans. The oceans are just sort of like soaking it up. And so how we've got to represent convection in the ocean and so forth. So how rapidly they take it up is a sort of critical timing aspect of climate change. They don't affect climate sensitivity that much, but the timing they affect a lot. Yeah.
So my point was, what is the quality of ocean modelling right now, and does that actually affect the quality of the climate change models? In other words, do we need to put a lot of effort into ocean modelling?
The answer is the biggest uncertainties come from the atmospheric models, but it's also important to develop the ocean models. The ocean models have a lot of detail of small-scale eddies that we really want to know what happens with them. The ocean also has important things like acidification that's happening to it that we really want to know about it. And an absolutely critical thing the ocean does is interact with the atmosphere to produce things like El Nino. Now, we've got to model that really well, which means we need really good quality ocean models, because sitting here in Australia, changes to El Nino is probably one of the most important things. Is that going to become more variable, less variable? Is it going to become more frequent? Is it going to become, what are the impacts going to be? So you can't develop one without the other. So yes, ocean model, absolutely critical. Yeah.
How is the model averaging done? Are the models weighted based on the performance?
To weight them?
Yeah, in average.
Yeah, and good question too. I mean, actually, there's a huge amount of research done there. What you could do, what I showed you here is just a dumb averaging. You get 24 models and you average them up. But of course, you might think, what about I test this against the current climate? This one's more skillful, I'll weight that more highly than this one that's, like can't do this well. And there's a huge amount of literature on that. But the problem is with climate models, you can test them in so many different ways. They might be really good at ENSO, but their monsoons are terrible. So how do you arrange what people tend to do is produce a basket of things and then try to weight them, but it's an unsolved problem how to weight them skillfully. And to be honest, it doesn't matter that much in the end, really. You just average them up, you get a fairly similar result to very sophisticated techniques. Yeah.
Michael?
So when I look at this 100-year outlook, or outlook to 2100, I think the situation is dire, but I think if I look at it from the point of view of a policymaker, I think the situation is dire no matter what I do. Right. In some sense, the only difference I can make is to my grandkids' generation, and so I wonder if there's any discussion in the community of considering more radical forcings or models, for instance, adding sulfur dioxide to the atmosphere to have some human modification difference in areas in which humans can play a role in that model, and whether those things should be included on that kind of a chart.
No, you've hit upon a whole area of research called geoengineering, and you can run your model and you can say, okay, well we know that put in a volcano, it cools it by half a degree. What if we were to pump sulfates up into the stratosphere? Or what if we were to put algal blooms and put iron filings in the ocean to simulate algal blooms and take up carbon and so forth. And so you can run these models with these kind of assumptions. And look, to be honest, it's actually pretty controversial within the science, because a lot of people think, look, we're that desperate, we really want to investigate these areas. But we know that if we were to do this, then we cause further modifications. Say you put further sulfates into the atmosphere, you're going to affect rainfall patterns, for example. You're not going to be able to do anything about, say, ocean acidification, because carbon dioxide levels will be the same.
So the question is the science controversial or is the policy controversial? From the point of view of the scientists should, I'm trying to understand what these things
and a lot of scientists will say, yep. Well, in fact, there's an intercomparison project out there which says, okay, let's put sulfates in these models and see what effect we get. And so, yes, it's in the literature and it's actively researched. I suppose, I would just anecdotally, I know some colleagues have some reluctance about this because they think that mitigation is the safer option. But yeah, it's something that should be presented to policymakers. In fact, there's a chapter in the upcoming IPCC which is about geoengineering. So it's going to go to policymakers to say, well, here's what we think are the future projections. If you were to do this, then here's what you might find. I would say, though, it's in its infancy. People are only just starting to run these experiments.
Most of the responses you still look at show there still look reasonably linear, in the sense that there's a broadly linear relationship between forcing and the resulting temperature rise.
Yeah.
I've seen plenty of things in the media about these ideas of tipping points, that the whole planetary system may in sense be essentially bistable, and that some fairly catastrophic event might occur, for example, large-scale methane emission from permafrost or something like that, and then drives it, makes the feedback loop. It essentially takes the denominator of feedback loop below zero, I suppose. Are those in the model, or are those actually relatively far-fetched concepts?
Some of those, like these are surprises, like a threshold, for instance, you might get. Some of these are in the models. For instance, there was a suggestion of what's called the thermohaline circulation, which is the deep circulation in the ocean. And the suggestion was if you passed a threshold of warming, the thermohaline circulation would shut down in the North Atlantic. In fact, shut down globally. And this circulation would stop taking place, so large-scale currents would stop flowing up to Europe and this sort of thing. This kind of thing is in the model. And models suggest that there'll be a thermohaline slowing, but not a collapse, unless you get very high forcing. Some aspects, though, are not in models. And for instance, if there's permafrost, if permafrost melting releases huge amounts of carbon or methane that are there frozen, that's generally not in the models because it's just not a processor that's put in there. So the short answer is yes, there's a potential for surprise and strong nonlinearities. Some of them are in the models, many aren't in the models.
Yeah, last question, please.
Yeah. One of the biggest problems that certainly I had in trying to convince non-scientists about the problems of global warming is that they don't see the connection between levels of atmospheric carbon dioxide and the temperature rise.
Yeah.
Now, am I correct in saying that it's because of the absorption of radiation by the carbon dioxide absorption spectrum, of the solar radiation coming in and coming out by carbon dioxide?
It's the terrestrial radiation. I really skipped over this. The physics of it's very well known. But what happens is if you increase carbon dioxide in the atmosphere, it will absorb a little bit of extra shortwave coming in, of solar radiation coming in. But its main effect is entrapping the terrestrial radiation that's going out. And of course, they say in the literature, well, CO2 bands are saturated. And in fact, they are. But the extra absorption that takes place is out in the wings of the CO2 spectrum. So in fact, the amount of absorption that takes place goes not linearly with CO2 amount, but as the log of the CO2 amount. So if you double carbon dioxide, you get 4 watts. You'd have to double it again, up to 4 times the amount, to get another 4 watts out of it. But we're very confident of this, but yes, there's misinformation out there saying, look, carbon dioxide doesn't matter, it doesn't absorb, it's just wrong, that's wrong.
This is all Arrhenius back in 1895.
What's that? Arrhenius, yeah. In fact, we've known about greenhouse, for more than a century. The basic physics of the atmosphere has been understood, but yeah.
I just want to be able to, when people say, there's no connection, say, well, no, it's something.
There's a lot of misinformation around about a lot of these aspects. So, yeah, it's an issue we deal with a lot. Yeah.
That's what gives you the 1 degree, right? And in reality, it's actually...
What's that?
That's what gives you the 1 degree Celsius per doubling, you were saying, from first principles.
Yeah.
And then in reality, it's even bigger than that. So, not only is that established, it's...
Yeah. Oh, yeah. Look, the 1 degree, I mean, in a sense, no one could really deny that unless you deny the physics of carbon dioxide absorption. Of course, sensitivity at the high end of the scale is going to be a lot more catastrophic, and so a lot of the debate takes place about other feedbacks. Yeah.
Okay. Well, let's thank Rob again for a very...